In this question, the variation of voltage and current of a semiconductor device during a switching transition is given. Okay, so this switching transition, it can be switching on or switching off. Okay, so that is the first question, whether the switching transient is corresponding to turn on or turn off. Okay, this is the first question. The second question is to find out the energy lost during this transition. Okay, now for a semiconductor device will act almost like a short circuit when it is in a switched on position. Okay, so you can see from this transient that the voltage, it is reducing from a constant voltage V to 0, right? So here itself you can say that it is a switching on transient. Okay, and also the current I, it is increasing from 0 to a constant value capital I. Okay, so the voltage is reducing to 0, the current is reaching a steady state value. This is the characteristic of a switching on transient. This is how the semiconductor device will behave when it is switched on. Okay, so the first question answer is the switching transient is corresponding to turn on. Okay, now what is the second question? You have to find out the energy lost during the transition. In order to find out the energy, we first have to find out the instantaneous power. Okay, and we have to integrate this instantaneous power. Now what is the instantaneous power? It is the value of the voltage at any time t into the current at any time t. Okay, so this is the instantaneous power P of t. The energy will be given as the integral of instantaneous power. Now from the switching transition we can see that before this time, okay, the voltage is at a steady state value while the current is 0. So the power, the instantaneous power at any time during this interval will be 0, right? And beyond this time, this is T2. Okay, so beyond this time the voltage is 0. So the instantaneous power at any time, it will be equal to 0. So what should be the instantaneous power? We have to find out. It is between this time interval. Okay, so if you take interval T1 first, okay, the voltage is constant at V, okay, while the current is time varying. Okay, then what is the instantaneous power at any time t? This will be equal to the constant V, okay, into I of t. Since I of t is time varying, we will simply write as I of t. And what about the interval T2? Here the current is constant, okay, and what is the constant value? I. And what about voltage? Voltage is time varying. It is varying with respect to time. So what will be the instantaneous power at any time t during this T2 interval? This is equal to I into V of t. Now if you integrate this instantaneous power, you will get energy only during this time interval. Okay, if you integrate this P of t, you will get energy during this time interval, and if you integrate this P of t, then you will get energy during this time interval. So we have to add them both to get the total energy that is lost during the transition. Okay, so here during interval T1, energy is equal to integral P of t. Okay, so this will be equal to integral V into I of t, P of t dt, right? V I of t into dt. Okay, so this will be equal to, you can bring the voltage outside the integral. Why? Because it is constant, it is not varying with respect to time. So we can get it outside the integral. So we have this. Okay, now here you have to observe that this integral I of t dt, this is nothing but the area under the curve I of t. Okay, so if you see the diagram here, this here will be the integral I of t dt. Okay, if you redraw this particular current here, you see that this is a constant value I and this time interval is t1, and we need the area of this triangle here, right? So the base is t1 and this will be I, right? Because this is the constant value of current I. So this is equal to capital I. So what is the area of this triangle? That will be equal to V into integral I of t dt is the area of this triangle, which will be equal to half into the base, which is t1, into the height, which is I. Okay, so this will be equal to Vi by 2 into t1. This is the energy during the time interval t1. Okay, for t2, the energy we will find in a similar fashion. This will be equal to P of t dt. This is equal to integral I V of t dt. Okay, here also you will take out the current outside because it is constant, and V of t dt. Now here also V of t dt is the area under the voltage curve. So if you see the switching transient, this here is the area under the voltage curve. Okay, so this is also forming a triangle. What is the base of this triangle? The base of this triangle is T2, right? This is the time axis. Okay, and the voltage, it has been constant at V. So from here you will get that this is capital V. So the height is capital V. So this will be equal to I into the area of triangle will be equal to half into the base is T2 and the height is V. Okay, so you have Vi by 2 into T2. Okay, so this is the energy during T1 and this is the energy during T2. So what will be the entire energy, total energy during transition? It will be the sum of both these energies. Okay, so the total energy during transition, switching transition, is equal to Vi by 2 T1 plus T2. Okay, so this is the answer to the second question.